Okay, everyone. I had some Zoom issues right now. My recording stopped, so I have to redo this. So I'm going to start over here. So it says in chapter 8, we're going to basically be dealing with hypothesis testing, and 8, 9, and 10 will all kind of follow a similar pattern to chapter 8. So you really have to understand chapter 8 to do well at 9 and 10, and maybe even 11. The thing about hypothesis testing is you have something where you kind of think this is the way things should be, and then you're going to try to find evidence against it, or the way society views that this is, and you're going to try to find evidence against it. But basically, we're just going to be trying to develop a technique that we can use to test claims about certain population parameters. Okay, so it says the main objective of this chapter is to conduct a hypothesis test for claims about a population proportion P, a population mean mu, or a population standard deviation sigma. So in general, that's what we're going to kind of stick to. There's other things that we could test, but those are the main three we're going to worry about. And it says, we can kind of go down here. Rare event rule. If under a given assumption, the probability of a particular observed event is exceptionally small, we will conclude that the original assumption is likely incorrect. So let's take a look here. We have the United States Mint is producing, they like to produce a fair coin. Basically, how many times, if it was actually fair and they flipped the coin 100 times to test this idea, would you expect to get heads? So we would expect to get heads 50 times, okay? So then in part A, it says, is there enough evidence to conclude the coin is not fair if the number of heads out of 100 flips was 52? So we would say no. We would say 52 is pretty close to 50, so we really don't have enough evidence to say it's not a fair coin. It's not exactly 50, but it seems pretty close. So we're not going to get into a big argument about that. However, if we get 97 heads out of 100 flips on a coin that's supposed to be fair, we have to start thinking, what's the probability that that actually happened? If it was a fair coin, it's very, very slim. So then we would assume that the coin was actually not fair. So we would have to go through and do a statistical test or a hypothesis test on that to see what the evidence says. But we can kind of eyeball it and say 97 seems like no way, right? So that's kind of the idea of the entire chapter, is to say, well, here's what it should be, or here's what people say, and we're going to do a test, and either we're going to find the contrary to that, or we're not going to be able to disprove the original claim. Like up here, 52 is definitely different than 50, but is it enough difference to say that, oh, it's not fair, it must be a false coin or a non-fair coin? No, we can't really say that. But with 52, can we say definitively that it is also a fair coin? No, we can't really say that either, but we definitely cannot dispute it. With 97, we can dispute it, right? And then we're going to learn how to do a test for that. Okay. So these formulas are very, very important, you guys, when you're making your little cheat sheet to take the test with. It is very, very important that you learn this. You also learn this. This is very, very important, okay, that you understand these ideas behind it. You may not actually need to write it down, the better you get at it, but for now you will refer back to this quite often, at least to look at it. Okay, so we're going to be talking about the null hypothesis, which I'm going to call H naught, and then the alternate hypothesis. So this is the null, and this is the alternate, right? And just to kind of, your book might use H naught, which is H sub 0, and then H sub 1. They might call H sub 1 the alternate. I'm going to, in general, use H alternate with an A. So it says the null hypothesis, a statement that the parameter of the population is at least equal to a specific value. This statement must always include the equal sign. So we will always have an equal sign. Okay. The alternative hypothesis is the parameter has a value different from the null. Either it's greater than, less than, or not equal to the null stated null hypothesis. So something that's going to be very important to us is talking about right-sided and left-sided, or right tail or left tail. And then we're also going to talk about two-tail. Now, the idea of two-tail we've already kind of worked with in confidence intervals. Remember when I would draw the picture, right? I would have this, and then I would say, well, we're going to cut this here and here. and then we'll shade over here, and we'll shade over here, and then we'll have a certain area over here and a certain area over here. So we've done this already. That's a two-tail test. So that's a tail that would have two tails in it with area on both sides, okay? So just a little bit of, we can do a few examples with this. It says, for each example below, state the notation for the null and alternative hypothesis. Make sure you are using P's for the proportions, mu's for the means, and then standard deviation sigma later on. So in 2003, young people age 18 to 24 had an accident rate of 12%. We are interested in whether the true proportion of young drivers having accidents has increased since 2003. Okay, so we have to think, what is the null and what is the alternate? So first, I normally write null, okay? So we know, are we talking about a population proportion or are we talking about a mean? In this case, it's talking about a percentage, so we know that that's a population proportion. I guess they could word it in a way that would make it the mean, but they're not doing that for this problem. So we're gonna say P is equal to what percentage? So it says young people age 18 to 24 had an accident rate of 12%. So we're gonna say 0.12, okay? Over here, we're gonna say H naught, or I'm sorry, H sub A, or the alternate hypothesis. They say we are interested in whether the true proportion of young drivers having accidents has increased since 2003. So we know that that means that has P become greater than 0.12. So that would be the null and that would be the alternate hypothesis, okay? The next one says H naught. We're gonna find that and we're gonna say H alternate. Let's do H naught and H alternate. It says a survey of study of habits of attitudes in a psychological test that measures students' study habits and attitudes towards school. The mean score for college students is about 115, okay? And the standard deviation is 30. A teacher suspects that the mean for older students is higher than 115. So once again, this is now talking about mean, not population proportion. And they told you for college students in general, it's about 115. The teacher suspects that the for older students is higher than 115. So this would be mu greater than 115. Okay, and it says one survey showed that among randomly selected subjects who completed 4 subjects or 4 years of college smoked less than a general population. The rate of smoking is 27% for the general population. So once again, is this talking about mu or P? Are we talking about population proportion or are we talking about the mean? Again, we look and we see, well, 27 means that we are dealing with the population proportion is equal to 0.27 and the alternative hypothesis would be less than 0.27. Okay. I'm going to kind of skip past some of these, you guys. I really want to start getting into hypothesis testing, so I don't kind of bog you down with this. You'll see how it works, and I do a 7-step process for it. It'll be a little bit different than what the notes does, so we might start having separate problems from the notes. So make sure you leave yourself some room to write other problems. So we're going to be able to find, moving forward, something called test statistics, okay? So test statistics is a statistic that compares the value of the parameter stated in the null hypothesis with an estimate of the parameter from the sample data. So this is something that we've done already, right? So large values of a test statistic indicate that the estimate for X bar is far away from the parameter of mu in the null hypothesis. Common test statistics are z-scores, t-scores, and chi-squared. So luckily, we know how to do all of those. I do want to say, you guys, that this is very uncommon. It can happen, but we will rarely use this one. Okay, maybe I should cross it out. Let me write it a little bit better. Very rare. And again, think about it. If you're talking about the mean and you're trying to do a test on the mean, I'm just saying it's very unlikely that you will also know the standard deviation, because if you did, then why are you doing a test on the mean? You already know it, right? So I know, I guess that's a bad way to explain it. It's just very uncommon that you know the standard deviation when you're doing a problem with the mean, okay? So basically, we're going to use these 3/4 formulas. So again, you must know these. You must be able to refer back to these, have these in your cheat sheet. Again, that one in yellow is more uncommon than the rest, but you should still have it written down. Okay, so we're going to use these repeatedly. Again, I'm going to show you how to do it in the hypothesis test. I'm going to give you a very structured way to do it. Hypothesis testing is a little strange, so I'm going to give you a very structured way to do it. So it says the p-value, this is another way to talk about the probability of observing test statistics that extreme or more extreme. The probability of observing test statistics this extreme or more extreme if the null hypothesis is true. This value measures how much evidence you have against the null hypothesis. Small p-values indicate outcomes measured from the sample data is unlikely to happen if the null hypothesis is true. Okay, so basically the p-value to us, okay, the p-value is, how can I summarize this? Probability of observing a test statistic, the extreme or more extreme if the null hypothesis statement, population parameter is true. So the p-value is trying to measure the evidence you have against the null hypothesis, okay? Small p-values indicate the outcome measured from the sample data is unlikely to happen if the null hypothesis is true. How can I explain this in a better way? Let me think about this for a second. What's the best way to explain p-value? For you guys, what somebody else says about it. I don't like this definition per se. I'm having trouble thinking about the best way to say it. So the p-value, let me put it this way. I don't like this definition either. So let me put it this way. Basically, the p-value tells you, if you have a very, very, very small p-value, okay, it tells you that that's the likelihood of the null hypothesis being true, okay? So if your p-value is very, 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 very small, like 0.00001, you know, which happens a lot, that means that that's the probability that the null hypothesis is actually true, okay? So the p-value then, if something has a very, very small probability of being true, then you would in turn reject the null and say, well, since my p-value is so small, I'm going to reject the null. So in general, if you have a very small p-value, you can reject the null, okay? I'm going to teach you guys how to do it the traditional way, and I'm also going to teach you guys how to do it the p-value way, okay? The computer and your online homework and tests will do almost entirely the p-value method, so we'll do that, you know, often in the notes, and I'll show you how to use the calculator to do that. But I also want you to see the traditional way, okay? Significance level alpha. So this is the p-value. Oops, that's not really nice. Significance level alpha, the decisive p-value we fix in advance, okay? So we're gonna have something called our alpha level or our significance level, and we're gonna oftentimes compare it to the p-value. And if the p-value is less than or equal to our significance level, we're gonna say that we're going to reject the null, okay? So that'll be kind of our way to base our decisions for hypothesis testing. This states when the null hypothesis should be rejected, okay? So it's like we give a threshold, okay? So this threshold is called the significance level of the test and is compared to the p-value above. Common alpha levels for rejection are 10%, 5%, or 0.01, 1%. If p-value is less than the alpha level, then we reject the null hypothesis. So again, in these problems, you will be given a p-value, or I'm sorry, a significance level in alpha, okay? And based on that alpha, you then can start saying, well, if my alpha is 10% and my p-value is 5%, well, since my p-value was less than my alpha, I'm still going to reject the null, okay? So this states when the null hypothesis should be rejected, all right? So as long as we have enough statistical evidence that is less than the alpha, we can reject the null, okay? So if our p-value is rare and falls below the threshold, below the significance level, we reject the null hypothesis, include our result is statistically significant. Okay, so basically saying that what we have found isn't by chance. This actually means something, and we're going to reject the null. Okay, so that's basically what we're working for. Now I'm going to kind of I'm going to skip this part right here for now because I'm going to do it in a problem. Okay, we're going to do this together, and I'm not going to use 5 steps. I'm going to use 7. Okay. Here's just a little bit. I don't go too heavily into this, but I wanted to talk to you guys about it. So it is important to understand that the results of the hypothesis test may be erroneous based on our sample data. So it is possible we could be wrong. Just like with everything, it is possible we could be wrong in statistics. It is good if we reject the null hypothesis that is false, that is in fact false, or if we fail to reject the null hypothesis that is true. So you guys understand that you could say that the null hypothesis was false based on your data, but there is a chance that the null was actually true when you said it was false, okay? There's also the chance that you don't have enough evidence to reject the null, but you should have, because it turns out the null was actually false, but you didn't have enough evidence to reject it. So that can also happen. So these are types of errors that can come up. So we have a type 1 error, the mistake of rejecting the null hypothesis when it is actually true. Oftentimes this is called a false positive. Okay, so the rejecting the null hypothesis when it is actually true. Okay, type 2 error, the mistake of failing to reject the null hypothesis when it is actually false. Okay, so I'm going to come down here, and you guys have a couple situations you can run into. So we have this situation where we reject the null, okay, but this says that the null is true and we rejected it. So this is called an alpha level, or this is a type 1 error. Okay, so we rejected the null, but we know that the null is true. See, that's a problem. Okay, here we reject the null. However, the null is false. So this is good, right? We know that the null is false. So this is a good thing. We did our job. Okay, so this is good. Now this one, it says the null, so we're here now, the fail to reject the null, and the null is true. So we're saying that we were trying to reject the null, but we didn't have enough evidence to reject the null, but it turns out the null is actually true. So again, we fail to reject the null, and null was true. So again, this is good. We did a good job. However, over here, we failed to reject the null, but the null is false. So fail to reject null, but null was false. So this means that we should have rejected the null. So this will be our, sometimes they're called beta level error. Now this is a, this is a type 2 error, beta right there. And then the first one we did up here was a type 1 error, okay? So these two situations right here are good. We did our job. Our hypothesis test did good, okay? The other two are actually bad. They're types of errors that we could make. And again, I'm not gonna go too crazy into this, but I just wanted to make you guys aware of it. So here's a situation that could happen. It says sometimes tests for disease are inaccurate. Let's say a patient goes in to be tested for a disease. A lab tech administers the test and gives the patient the results. So let's assume the null hypothesis is that the patient is disease-free. So we know right now the null is disease-free, okay? And then the alternate has disease, okay? So it says write the null and the alternate hypothesis in words and determine type 1 and type 2 errors. So what would a type 1 error be? So let's look at type 1. It says the mistake of rejecting the null when it is actually true. So what we're saying is we're going to reject that they're disease-free. So we're going to say doctor says has disease when actually when patient is disease free. Okay, so this is why it's called oftentimes a false positive. Okay, so the doctor says they have the disease, but in fact they don't. They made a type 1 error. Type 2 error. Okay, type 2 error says that the mistake of failing to reject the null when it is actually false. Okay, so we're failing to reject the null. So we're going to, I'm going to say, let's fail to reject null. Okay, so what does it mean to fail to reject the null? So we want to say that they are disease. We want to reject the null and say that they have the disease, but we don't have enough evidence to say that. So we're going to say, let's see, doctor says disease free, but it says up here, it says when it's actually false. So that means being false for disease free means you have the disease. So says disease free, but has the disease. Okay, so these are type 1 and type 2 errors. I'm not going to go too much into that, but I think down the road, if you take more statistics class, you will have to worry much more about that. For us, it's not going to come up too often. Okay, so I want to take this minute to come over here, and I'm going to give you guys my own problem. I actually used to teach it when I first started teaching statistics the way the notes does. But I found, I watched a video on different ways to teach it, and from Professor Leonard, the one that I gave you guys videos on, I actually like his method a little bit better. So I'm going to give you guys a problem, and we're going to kind of go through the 7 steps. So 7 steps for hypothesis. Okay. So this will be separate from your notes. It's very similar to the ones in the notes, but so I'm going to kind of go one by one. So step 1, okay, create. Oops, you know what? Let me give you guys a problem. So it says a sample, and like I said, I feel like the best way to teach this is to do examples of it. A sample of 706 companies found that 61% of CEOs were male. Okay. The researcher states their belief that most CEOs are male. Okay, so we want to test this claim. Let me see, what type of significance level do I want to use here? Let's use 5%. Okay. So in general, the significance level will be given. If it's not given, just like before, assume 95% confidence level. So assume significance level of 5% if it's not given. So here's what we're going to do. So it says a sample of 706 companies found that 61% of CEOs were male. The researcher states their belief that most CEOs are in fact male. So we want to test this claim with a significance level of 0.05. Let me clean this word significance up. Okay, so let's go. Let's do this. So it says, so here's how I want you guys to set these up. So I want you guys to set it up with the claim and the opposite claim. Okay, so this is how I want you to start every time. Okay, now again, if you're doing the exam and the homework online, they won't require you to do this, but I want you to kind of do this in the beginning to kind of get your bearings and see how you're working with all of this. So what's the first thing that you notice is the claim. Okay, the claim, test this claim with a significance level. The researcher states their belief that most CEOs are male. Okay, so let's see, is this a population proportion or is this a mean? Okay, well, this is a proportion, right? Because it's a part of the population. How many? Not the average number of CEOs, nothing like that. It says that 61% of CEOs are male. Okay, so the claim is not that 61% of CEOs are male. The claim is that most CEOs are male. So now what you have to decide is, what does most mean? What does most mean to you? Okay, well, most means more than 50%, right? So we're going to say the probability or the population of CEOs that are male is more than 0.50. Okay, so then the opposite claim has to be less than or equal to 0.50. Okay, so the claim and the opposite have to account for every single value, every single possibility, okay, from 0 to 100%. So the top claim says that it's greater than 50%. The bottom claim can't say that it's less than 50%. It has to say it's less than or equal to 50%. One of them has to have an equal sign attached to it somehow, some way, okay? So now the second thing we're gonna do is we're gonna decide, or we're gonna build our, let me see here. The second thing we're gonna do is we're going to build our null and alternative hypothesis. So you should just write null and alternative like this, okay? Now, the null hypothesis always has to have the equal sign. So whichever one of these has the equal sign, that is the null. So we notice here that this has a less than or equal to. So what I'm gonna do is I'm gonna say that P equals 0.5. Notice I got rid of the less than part. So the null will always be the one with the equal sign, but it'll just be equal. You don't bring the less than or the greater than with it. You only write it as equal, okay? Now the alternate hypothesis is the other guy, greater than 0.50. So in this case, this guy was this one and this guy was this one. It won't always be the way. Sometimes the claim will be the null and the alternate, and the opposite claim will be the alternate hypothesis. Okay, so we have that. The third thing I want you guys to do, maybe I should do this. Yeah, maybe I should put little lines in between. So the third thing I want you guys to do, you know what? I think I know how I can make this a little bit more or simpler for you guys to see, is I should write it so we can see step 1, step 2, step 3. This will make it a little bit nicer for you guys. Okay, so the third thing I want you to do is I want you to state your alpha. In this case, we know alpha is 0.05. Okay, and then I want you to tell me if this is a left tail, a right tail, or a two-tail test, okay? So here's the thing. The alternate hypothesis, you know what, let me write it over here. The alternate hypothesis tells you what type of tail test or direction test. Okay, so we're going to look at this and we're going to say, well, so let me just kind of give you guys 3 situations. Okay, now again, you don't have to do this. I'm kind of doing this as a teacher. So let's say we have 1, 2, 3 situations. Okay, so this would be the null hypothesis is, and this could be any problem, whether it's P, mu, or sigma. I'm just doing it for this particular one. P is greater than 0.50. We could have had the alternate. BP is less than 0.50. Let me clean this up. Okay, so alternate. P is less than 0.50, and P is not equal to 0.50. Okay, those are our three choices for our alternate hypothesis. And again, if you're wondering where I got this from, I come back up here. And remember, I told you guys way in the beginning. So here we go. We have our, let's see here, alternate hypothesis, alternate hypothesis, alternate hypothesis. Okay, alternate hypothesis. So these are basically, I'm doing a little brief summary for you guys of that. Okay, so let's go back over here. So now the shading. So because this is a greater than, we're going to shade this way. So that would make it right tail. This one is less than, so that's going to make it this way. That makes it left tail. Okay, and this one is not equal to, right? So that makes this one two tail. Okay, so that's how you decide. The alternate hypothesis always dictates if it's a left tail, right, or I guess you could say left direction, right direction, or two tail, two direction. Okay, and so this is how you decide for the particular problem what you're working with. All right, so in our case, what are we dealing with? A right tail, left tail, or two tails? So take a minute, think about that. Well, we go up here to our alternate hypothesis, and we are dealing with a right tail. So we are dealing with this guy. So this is the one we're going to use. Okay. And for each problem you do, you don't have to write all three of these out, but you do have to tell me if it's a right tail, left tail, or two tail test. Okay. So now we're going to go on to part 4. Oops. Let's do part 4. Okay, so let's see here. Part 4 would be test statistic. So now we have to find the test statistic. So now I'm going to go back over here, and I'm going to say, because we're dealing with population proportion, this is how we're going to find our test statistic. Okay, so we could also go up here and look at our formulas that I gave you earlier. That's the same formula as right there. Okay, so we have p hat minus p divided by the square root of p q divided by n. Okay, so let's go over here. So we're going to do our test statistic. So remember, our z is equal, our z is equal to p hat minus p divided by the square root of p times q divided by n. And let's just make sure we double checked and did everything right. So p hat minus p over the square root of pq over n. So p hat minus p, okay. So in our problem, what is our p hat, okay? What is our p hat? A sample of 760 companies found that 61% of CEOs were male. So in this case right there, they just told us that the sample had 61% male. So that is our p hat, okay? Because remember, we're talking about the percentage of the population that has male CEOs. So our p hat is 0.61. Now what's our p? Well, you always get this number from the null. The null says that p equals 0.50. So I'm going to say p equals 0.50 because the null says that p equals 0.50. Now we're going to divide that by the square root of 0.50 times, well, if p is 0.50, what's q? 0.50. And then n was 706. Okay, hopefully you guys are okay with this so far. Okay, so let's take out our calculators and plug this in. Take a minute, pause the video, make sure you get the same answer as me. So this would be 1 divided by 0.25. So yeah, I get 5.84. Let's just go 5.84. You know what, let's go 5.85. Let's round to 2 decimals for now. Okay, so that is our test statistic. Okay, so that's step 4. Here's step 5. Step 5 says, okay, step 5. So what we want to do in step 5 is draw a picture. Okay, so we're going to do this. We're going to do, now remember we're doing z-scores, so we have our normal curve. Okay, so where would you guys, so we draw our picture. Now here's the thing, we're doing the traditional method right now. Okay, I'll show you how to do the p-value method. Okay, so the traditional method says that you first find the critical value. So find okay, in this problem, remember alpha was 0.05, correct? So we then go over here. Were we dealing with a left tail, right tail, or two-tail test? Remember, we were dealing with a right tail test with 5%. So we're going to come over here. We're going to do a little line right here. This is 0.05. We know that the area in there is 0.05. So we need to find a z critical value. So z crit value for 5%. Now you cannot use the table that I gave you, or not the table, but remember in chapter 7, I gave you for confidence intervals, common critical values. Well, those were for z alpha over 2. That's if it were a two-tail test, but this is only a one-tail test. So what we have to do is we're going to do, let's see here, second vars, inverse norm. And if there's 5% on the right, then I know there's 95% on the left. So I'm going to do 0.95, and I will get 1.644. So let me write this as 1.645, I guess. I think that's one of the ones for the critical table, but that was with 10%. And that was because you were cutting it in half. So we have 1.645. Okay, that's our critical value for a one-tail, right tail test with 0.05. Okay, now here's all you do with the traditional method. Okay, so the traditional method says you have 5.85 as your test statistic. Where would 5.85 be located at? 5.85 is way over here somewhere, right? Here's 5.85. Okay. Right, and this goes on forever and ever and ever. So 5.85 is way over there to the right, okay? So something I want to tell you guys is this area, oops, let's do this. This area here, this is the fail to reject region, okay? So anything that falls in this area is fail to reject, all right? Anything that falls in this region is called the rejection region, okay? So in the rejection region, you reject the null. In the fail to reject region, you fail to reject the null. So this is fail to reject the null, and this is reject. Okay, so the reason you draw the picture is wherever you shade, that is your rejection region. And if your test statistic falls in your rejection region, then you reject the null. If you reject the null, that means you accept the alternate hypothesis, okay? Now the catch is, if you fail to reject the null, you cannot say the null is true. It's just simply saying you don't have enough evidence to disprove the null, so you're not going to say it's false. So in general, you can only ever you can only ever reject the null and say that the alternate is true. You can never really say in our problem that the null is true, even though it may be, or it may be discovered later on, or you know, that the null turns out to be true, or there's evidence to suggest it's true. You can't definitively say it. However, if you reject the null, you will definitively say that the alternative hypothesis is true. However, once again, could you be wrong? Yes, because statistic allows for error. Okay, so it is possible that you could have made a type 1 or type 2 error depending on what you're working with. Okay, so far I have a fail to reject the null and a reject the null, and I have these two regions. So where does 5.85 fall in? Well, 5.85 falls in our 5.85 falls in our rejection region. So what we're going to say in step 6 is our conclusion. I shouldn't say our conclusion, our decision. Okay, so this is our decision. So we're going to say, since 5.85 falls in our rejection region, we reject the null and accept the alternate hypothesis. Okay, so now this leads us to step 7. So this is the final step in our 7-step process, conclusion. Okay, so this is our conclusion, all right? So in our conclusion, we now have to reword the problem. Instead of just saying we reject the null and accept the alternate, we have to say what that means. So we say there is sufficient evidence to support the claim that, now let's look up here. What was the null and what was the alternate? So the alternate said that the population proportion of male CEOs was greater, right? It was greater than 50%, which means most, right? More than 50%. So based on our statistical analysis, based on our test statistic from the sample, okay, and comparing it to the population, says there is sufficient evidence to support the claim that most CEOs, okay? So this is kind of your template for how you do these problems. So there is sufficient evidence to support the claim that most CEOs are male, okay? And that's how you can do a problem, all right? So let's see if we have another one. How long has the video been so far? Let me see. You know what, guys? I might just send this one out to you to kind of give you a chance to look at it before class today. And then we'll do some more in class today. So I'm going to go ahead and end this video for now. And I will see you guys in class or talk to you in the next video.